Hello everyone, this is Chandrakant Mishra. Today I am going to teach AC analysis. The AC analysis here will discuss the steady state response of networks or circuit to sinusoidal input. Sinusoidal input means your sine wave or cos wave. And you know the signal is periodic. So you have, let's say, some voltage Vm sin omega t, and this you can draw like this. That is, if you start from 0, but actually sinusoidal analysis we assume that your voltage or current has been applied to the networks from very long time. Here the time period, or it repeats, the cycles repeats for a fixed durations, that is called the time period. So you can see this sin omega t keeps repeating this pattern, and this one repetition, the duration of the one repetition is called the time period, and the reciprocal of that duration we call the frequency of sinusoidal wave. Here Vm from 0 to peak value, that is peak of the wave, called the peak value of the voltage or maximum value of voltage wave. Omega is the angular frequency, and you know it is its unit is radian per second. Omega is related to the frequency 2 pi f or time period 2 pi upon t. Let us say we want to compare our reference here, whatever we have put, that is a Vt equal to Vm sin omega t, with another voltage V1 t equal to Vm sin omega t minus phi. Phi is greater than 0. This represents the lagging wave, and let's say another voltage wave V2t is equal to Vm sin omega t plus phi, which represents a leading wave, and your phi again greater than 0. How to represent the leading and lagging? See here, this is your lagging, first one V1t is the lagging. See, the wave was starting before, that is your Vt starting at the 0 reference, start from 0. If you take the reference from here, so now the starting point has been moved to this, right? So this distance is the phi upon omega, that is t. This is the delayed. So in sinusoidal we call it lagging wave, because it lags the original wave by a phase angle of phi or a time of. Normally lagging and leading is property, or you can say is with respect to the phase angle. Same compared to come back to the V2t, where we see that the wave has been moved by a time of phi upon omega, and this is because it is starting point. If you take the reference, if you compare with the reference if you compare here reference with reference, you can see that this is lead by an angle of phi, where phi equal to omega and time advance. We'll use these notations. Small vt denotes the instantaneous value of quantity, Vm peak or maximum value of the quantity, dc vdc, capital V dc denotes the average value, and or sometimes we call the V average, then capital V effective or Vrms denotes the RMS or effective value of sinusoidal wave. Let us move to the average values of a wave. Average values of a periodic wave is defined as 1 upon period, and integration over the period Vt dt. For sinusoidal wave of Vt equal to Vm sin omega t or Vm cos omega t, both the case, when you calculate the Vdc by using this definition 1 upon t, then minus t by 2 to t by 2 or 0 to t, any period. That's why I have not mentioned. So over a period, that indicates the over a any period. So minus t by 2 to t by 2 Vm sin omega t, right? So 1 upon t into minus Vm upon omega when you integrate, then cos omega t, t by 2 to minus t by 2. So you can see that this will be 0. Okay, cos pi and minus of cos minus pi, because your cos omega t by 2. So cos omega was your 2 pi upon t into t by 2. So cos pi, similarly this side will be the minus cos pi, definite integral. So minus 1 minus of minus 1, so minus 1 plus 1, it will be 0. So average value is 0. Same way you can try for ideal half wave rectified sinusoidal wave. You will have the average value Vm upon pi. You can do yourself. For full wave rectified sinusoidal wave, you have 2 Vm upon pi. Then come to the root mean square RMS value or effective value. Vrms square is equal to 1 upon t over a period v square t dt. For sinusoidal wave, Vrms is equal to Vm upon root 2. Same process you can proceed. I will do this one. Same way half wave rectified sinusoidal wave, Vrms equal to Vm upon 2. For full wave rectified sinusoidal wave, Vrms equal to Vm upon root 2. Let us calculate the RMS value of sinusoidal wave. Let us we have a voltage wave of Vt equal to Vm cos omega t. We want to find the RMS value of this. So by definition, Vrms square is equal to 1 upon 2 integration over a period v square t dt. So put these values. So 1 upon t over a period, I will take 0 to t, no problem, 0 to t Vm square cos square omega t dt. So Vm square upon t integration 0 to t. From basics of trigonometry, I know this cos square omega t can be written as half 1 plus cos 2 omega t dt. That will give you the Vm square upon t integration, whole integration 0 to t half dt, then plus 0 to t half cos 2 omega t dt. You just recognize this is the another sinusoidal, and you know that average value of sinusoidal wave is 0. Or you can calculate, you can verify Vm square upon t. This is the half into t, t cancel. So you have Vm square upon 2. So Vrms is equal to, because we have calculated Vrms square here. So Vrms is equal to Vm upon root 2. Quite easily done. Same way you try other cases also. For half wave rectified sinusoidal wave, Vrms is equal to Vm upon 2. You can calculate the same way I have already demonstrated. For full wave rectified sinusoidal wave, VRMS will be Vm upon. Now come to the form factor. Form factor is defined as RMS values upon DC value of full wave rectified. RMS value upon DC value of full wave rectified wave. If we take the sinusoidal wave, RMS value of sinusoidal wave is the Vm upon root 2 and the DC value of full wave rectified wave is the 2 Vm upon pi, that is pi upon 2 root 2, which is 1.11. Right? See the definitions: RMS, VRMS value and the VDC of full wave rectified wave. This is your full wave rectified wave. I have already given the expression for the VDC of full wave rectified wave, which is 2 Vm upon pi. Crest factors or peak factors, it is defined as peak value upon the RMS value. So for sinusoidal wave, peak value is the Vm, RMS value is the Vm upon root 2, which is root 2 1.414. So let us try this example. What is the average and RMS values of wave shown below? Let's say it is a voltage wave. In the positive side, the amplitude is the 4 volt and the negative side amplitude is the minus 2 volt and t is in the millisecond. So time period is 2 millisecond. Average values is the VDC 1 upon t, by definition 1 upon t over a period minus t by 2 to the t by 2 Vt dt. You can clearly see that this is the integration, is the area with the sine sense. So this area and this area with sine sense. So 1 upon t, that is the one period is the this. So 1 upon 2 and this area is the 2 into 1 millisecond and this area is the minus 2 into 1. I mean area with sine sense, positive or negative sense. So here the negative area, that is minus 2 into 1. So you get the 1 volt. Let us try with the RMS values. VRMS square 1 upon t over a period b square t dt 1 upon 2 0 to 1 4 square dt plus 1 to 2. You can see 1 to 2 minus 2 square dt. So half. This gives you the 16 and this gives you the 4, that is 20 upon 2, that is 10. This is not the RMS, this is the RMS square. So VRMS is the 1 upon root 2, 1 upon root. Let us move to the phasor notations of sinusoidal waves. Why we require the phasor notations? It is uncommon to employ complete sinusoidal wave equation in the circuit analysis, like Vi equal to Vm, let's say 10 cos omega t, 10 then some current in the other part of the circuit, I equal to 20 sin omega t milliampere, like that. So it is cumbersome to analyze. So we record a shorthand notations, and that notation is called the phasor notations. To analyze the circuits at steady state, phasor notations is known for the analyzing circuits in the steady state. It is most convenient form of analysis in complex circuits or networks. Both sine or cos can be chosen as reference. That means first you need to choose a reference. If it has been given, then you have to stick to the reference. So how to represent the input sinusoidal into phasor notations? We'll go by step. Vt equal to 20 cos omega t be the reference. In phasor notations, I can write, see, this is the amplitude and the phase is 0 phase. So I can write 20 0. That indicates that 20 e raised to the power j0. And you know, e to the power j theta Euler's identity, cos theta plus j sin theta e to the power minus j theta, which is cos theta minus j sin theta. So you have, let us compare. This is the reference. We have taken the reference as the cos omega t. Let us, you have another voltage V1t equal to 5 sin omega t. So you have to manipulate this, convert this in the cos form. So using the trigonometric relations. So I know I can write 5 cos omega t minus 90 is same as the 5 sin omega t. So this in phasor notation 5 angle minus 90, or I can write 5 e raised to the power, same, both notation same. When you open it, 5 into cos 90 0 minus j sin 90 1, so minus j5 is the same. This is called the Cartesian form representation of Cartesian form phasor representations. This is the exponential form phasor representation, exponential form phasor representations. Let us another voltage V2t 12 cos omega t plus 30. So I can write like this. If you represent in the Cartesian form of phasor representation, just use these relations. Let us have another V3 10 sin omega t plus 60, but our reference is the cos, so I have to convert into the cos. So 10 cos omega t plus 60 minus 90, so I got the 10 cos omega t minus 30. Let us move to the phasor diagram. What is the phasor diagram? It is a two-dimensional vector diagram that represents the phasor relations among the different currents voltage in a given circuit. It is drawn on the S-plane, or we call the complex plane. What is the S-plane? You know this from the control system if you have already studied. So this is the real axis, this is the imaginary axis or J. So here real quantity, here purely imaginary quantity, in this positive real, positive imaginary. Then this axis negative real axis, so negative real, positive imaginary, and this region is the negative real and negative imaginary, which is minus j here. So in our earlier example, this is the input voltage V1, that is your it is input voltage V is your reference, that is 20 cos omega t, so this is your 20. Okay, then this is the V1, phase is minus 90. See, V1 phase is 5 minus 90 degree. So minus 90, how to represent the degree? So degree, please remember, degree is always measured from the real axis anti-clockwise. That is 30 degree, 60 degree, 90 degree, this. Then negative from here, minus 30, minus 60, minus 90. So you know the argument always is in between the, accordingly you have to convert the angle. For example, suppose they have been given that like this. Let's say one phasor has been given like this, 270 degree. This is the wrong representations, though it is literally correct to represent, but as we are representing in the exponential or complex notations, for that we have to make the angle within this range. So you know 270 means 90, 180, 270, which is minus 90 is, you can write minus 90 degree. This is the correct valid representation, so can easily visualize.